Okay, second section of 6.2. This time we're doing confidence intervals for means, but this time with small samples according to the textbook. And we learned last class that if we have a known standard deviation sigma, there's absolute agreement that we must use a z-interval. So if we have that choice. And this is because we have continuous data that we can do this z-interval. We need it to be random, we need it to be independent, and we need it to be nearly normal. And the fact that it's nearly normal allows you to use this critical z or critical t, which we're learning today, distribution. In this textbook, they assumed that in section 6.1, they assumed that if CLT was met, which was over 30, then this textbook assumed that you could use a Z for that situation. It's more generally accepted that you would use a T whenever there's unknown standard deviation, but absolutely have to use Z if it's known standard deviation. But so I'm going to generally use a T whenever I have unknown standard deviation because of that best practice. Now, the thing about T is it's very robust because it's based on samples. So it actually can still work even when data isn't really perfectly normally distributed. In this textbook, we'll assume that any sample where when you're under 30, that is approximately normally distributed, which means it has one mode and basically is symmetric, we'll assume that the T is applying. But in fact, in real life, T intervals will actually work for even slightly to moderately skewed data because they are called robust, meaning they're really strong in the face of adversity. So they can work even at small sample sizes of say 15, 20, where you've got some skew. Under 15, you generally don't want to have any skew because you have such a little sample size. But the only time that they wouldn't work is if there are outliers. That's a critical time. Now, in this textbook, when they say something is skewed, they're going to mean it's highly skewed. And if data is highly skewed, or there are outliers, then you cannot find a confidence interval and you'll get to stop. You'll get to stop the problem and just say, confidence interval doesn't apply, or cannot find confidence interval. Okay, so in general, when sigma is unknown, we're going to use the sample standard deviation as the best point estimate of sigma. And when the sample size is large enough, critical t values actually get closer and closer to critical z values. That's why you'll see many texts use the z intervals for sample values greater than 30, even when sigma is unknown. Again, it's generally preferred to use t when sigma is unknown, and that's what I'm going to do. So, what is the best unbiased estimator of the population mean mu? That would be x bar. What would be the best point estimate of the population mean mu? I'm not trying to trick you. It's still x bar, the sample mean. So for all you, well, someday you'll get to try Guinness beer. And it was one of the master brewers, William Gossett, who lived back in the late 1800s, early 1900s. He was brewing beer and he was having some difficulty using critical Z's to try to figure out how to make the beer better. And he realized that if he could increase the width of his window for his intervals, he could get a better idea of trying to capture that true mean and trying to get a better idea of what his beer was really doing. So he was not only the founder of making Guinness beer into the kind of beer that it is, he also made a huge contribution to statistics by developing this, what we call the student T distribution or T distribution. If you look at the formula for the T statistic, like our Z statistic, it looks a lot like our Z-score formula, which was like this. And then, of course, we had our standard deviation. And then we learned in chapter 5 that if we have means, we need to correct that standard deviation, the standard deviation of the sampling distribution. We need to correct that. So if you look, this formula is actually pretty much the same as the T formula. The difference is that one of them is using known standard deviation and the other one isn't. And these are not really equal to each other, but they're similar to each other. Similar. And that denominator, that's based on the central limit theorem, because we're doing groups. We're taking samples and putting those samples together and finding their average or whatever we're doing with them. So student T or T distribution, the curve changes depending on how many items you had in your sample, n being equal to your sample size. So you have to find how the degrees of freedom, because that'll help dictate the curve for the T. So like if you think of a normal distribution as being something like that, then you're going to have a T distribution is going to be a little bit lower and a little bit wider. Oops, well, that didn't center very nicely. They're supposed to both be centered. Let me try that again. Okay, here's my normal curve. This is, okay, let's have the mean right in the middle here. So I'm going to try to make a wider and shorter curve. Dang it. And that would be a T. And then as my T's degrees of freedom gets lower and lower, this curve gets wider and wider and shorter and shorter. So this might be a degrees of freedom of 2, and maybe this one, the green one, might be degrees of freedom of I don't know, how about 20? And then that green, the blue curve could be a Z, or you could think of it as a T with maybe degrees of freedom of 999. It actually would be pretty darn close to being a Z. So the command that we use to find this, because these T distributions change depending on the degrees of freedom, we're going to have to put that degrees of freedom into the formula, and it's going to tell us what's the critical T value using the inverse T, which is like inverse norm, but has a degrees of freedom, so because it's changing constantly. Where do you find that? You find that right above the vars. You have to hit the second key. You have to hit the plus of vars key because you're really trying to get to the word distribution right above it. You want to get in there, and it's like probably the 5th one down, something like that. If you have a very old software package, you might be missing that command. So we're going to find the critical T value for a 95% confidence interval. So 95% confidence. Remember that it's 0.95 is in here. So my alpha outside is 0.05. I have to split that alpha in half. And so when I split it in half, I get an area of 0.025. Now I'm going to find the critical T for if n is 20, I get degrees of freedom of 19. So I have to go to the table and find, go to the table or go to my calculator. And so I am going to inverse T, 0.025. And I know it's going to come out negative, but I'm just going to call it positive. So my critical T for a 0.05 that's been cut in half with degrees of freedom of 19. See how I put those in my subscript just to tell the person? And let's go to the calculator and see what that is. Okay, second bars to get to my distribution. I have inverse t as my fourth option. I'm not sure where it's on yours. And now I have to put in the area, 0.025, comma, and yours is going to walk you through it by saying area to the left, by saying what's your degrees of freedom. Mine, I have to enter it into the order. And I got a 2.093. So I'm going to write that down. All right, now let's do that again. Same 95%, because it is definitely our favorite. I don't really need to draw all this. Why am I doing this? I don't know. But my degrees of freedom this time is going to be 40 minus 1, which is 39. And then the beauty of the calculator is that I can do an inverse t for any degrees of freedom that I want. And really this area out here is 0.025. So I have to put 0.025 in and 39. And let's go to the calculator and find out what a critical t for a half of a 5% with 39 degrees of freedom, what will that value be on our calculator? Whoops. Okay, and I get, and remember I just go with the positive, 2.023. Whoops, I've already forgotten the number. 2.023. And so then this textbook would have gone with a Z at that level. However, if you think about it, that's a little bit wide because remember what your critical Z for that level was a 1.960. So this does make a wider interval. This textbook is saying, well, this is wide enough, but in fact, it would be slightly wider. So that's why general practice, people would be using the T to make their interval wider. So the next page, I have that same table that we had in our notes last time that shows the critical Z's at the very bottom. And this shows some T values. What if I was using this table to do a critical T at a 95%? So here's my 95% down here. So I'm going to be in this column right here. If I was to use this table to do that, you can see that there's 30 and there's 40. Now 40 is actually too narrow. If you were going to use this table, you would actually use the more conservative level of 30. So if you were trying to do a sample size of 40, which is 39 degrees of freedom. So if you're trying to do 39 degrees of freedom, if you were using the table, you'd want to use 2.042, not the 40 because it's too narrow. Better to be too wide than to be too narrow. But this textbook would have allowed you to use the Z value. But I would just assume use the inverse T because then you can get the exact value for whatever degrees of freedom you have, and you would avoid the confusion. So here's our margin of error. Notice how the margin of error formula looks pretty darn similar, whether you used a critical Z or a critical T. The difference is that in Z you had known standard deviation, in T you're using the sample standard deviation, and in T you needed the degrees of freedom to help you find that number for the critical T. And then our confidence intervals and our point estimators are calculated the exact same way as we saw in the last unit. So we'll be doing those same things as last time. The only difference is we will have to think about our critical T or critical Z. So let's see what we have here. We have a biology test. It was administered to 50 students. So we have N equal to 50. The test had a sample mean of 77.6%. So in this, you can keep it as 77.6. If you want to use units, your units will be percent. Okay, so if we want to keep it as a percent, we can. And a sample standard deviation of 14.2%. Sample standard deviation. So that is a sample value right there. Whoops. Why did I write the... How come nobody said anything? There. Okay, so my sample mean and my sample standard deviation. Okay, when examining the histogram of the data, the shape appeared slightly skewed left, but no outliers. Remember, I said that slightly skewed will be okay. In the textbook, if you see something skewed, they're going to mean highly skewed. We're interested in a 95% confidence interval. So, is it random? Is it independent? Is it nearly normal? And I could say yes to all of those things because I would say if you had more than 50 biology students at a large college, there would be. And if it was nearly normal because they said that it had no outliers, but also CLT was met. So that's why this book would have gone with a critical Z. However, because we are using a sample standard deviation, I would like to see you use a critical T. So we're going to have a critical T. Critical T is preferred since sigma is not known. Okay, so because of that, let's do our, we're doing 95. So we've got 95. We don't really need to draw this, but I don't know why I just love that curve. You know, what a great curve. My degrees of freedom will be 50 minus 1. So if I was using the table, since I couldn't use 50, I'd use 40, but I don't want to use a table. I'm going to use my calculator. And then I put in my area, 0.025, comma, 49, and I get a critical T for a 0.05 that's been divided by 2 with 49 degrees of freedom. I get, where did I put my paper? Where I wrote it down. I got 2.010 because it was 2.00958. So I'm just going to call that 2.010. Okay, now let's find our margin of error. So now at least it goes right to where looks a lot like our critical Z, but we're going to be using sample value. Okay, so using that number. And I mean, I have it on my calculator. I probably would actually use the actual number that I have for my calculator. Gotta put in the sample value. Since I'm decided that I'm gonna have percents be my units, I can keep it with the percents, and I end up with 4.036 as my margin of error. Units on this margin of error would be percents, because I decided to just keep it in percents. And so my confidence interval, adding and subtracting my error, would be 77.6 plus or minus my 4.036. All of this being in percents. If you wanted to do it in decimals, you could, but I get 73.6% as the low value for the test. These are means. So means have units, and 81.6% being the high value. So with 95% confidence, the interval from 73.6% to 81.6% captures the true mean score on the biology test. And this biology test must have been administered to at least 500 students. And that 50 in the initial problem, that was a sample of students in a large school where they have hundreds of kids in the bio classes. And we're trying to estimate how are these hundreds and hundreds of kids, what's our best guess at their biology test scores. Okay, next problem. Let's try it again. So we have a simple random sample of movies, 25 movies to be exact, and we have a mean running time of 118 minutes. And I'll just say that also I had 25 movies. So at this level, this textbook would agree that this is a T. You'll notice that the homework I put an answer key so that you could check your answers, because the book won't always agree with what you get. So make sure you check your answers against my answer key. And the standard deviation was a sample value of 15 minutes. The shape of the data does appear bell-shaped with no outliers. That's your evidence that this is nearly normal enough that we can proceed. So we would need something that was random, as it was stated. We would know that this was independent, which we do know that 25 is less than or equal to 10% of all movies. Wouldn't you say there's more than 250 movies? Yeah, I mean, I've been watching a lot of them on Netflix. Okay, and then is it nearly normal? Yes, that's what the shape was described. Shape was nearly normal. Shape is bell-shaped. That's nearly normal enough for a T because they are so robust. So we are going to use a T. Let me write critical T. Some of your quiz questions will just say, which one would you use in this situation? Critical T. And they didn't, 95%. So I'll just write the alpha. This time I'm not drawing the curve. And I am going to put in my degrees of freedom will be 25 minus 1. So 24 will be my degrees of freedom. So an inverse T for a 0.025, because remember I had to cut that area in half, for 24 degrees of freedom, giving me a critical T of 0.05 divided by 2, 24 degrees of freedom, I get remember it comes out negative, but I'm going to just call it positive, 2.064. Bring that number down to the margin of error. My error will be that critical T times the standard deviation of the sample, and divided by the square root of n, so that's correcting it. And actually, we can do that calculation because of well, it's because it's independent that we're able to do that, just so you know. And then we had 15 was the standard deviation, and we had 25 movies, so I got to bring 25 back into action. And that gives me an error of 6.192 minutes, which then goes down to the next calculation, where we take that error and add and subtract that error to the mean that we got from a sample. This will give us a window of what we think might be true about movies, but we could be wrong. 111.8, 124.2, and so those were minutes, just to remind you, because when you get down to the context, it's so important to have the units. And so with 95% confidence, the interval, notice how I'm going to give the low and the high number. The true mean, what are we describing here? Movie running time? Movie running time. It's a good thing there wasn't a Bollywood movie in there, because that probably would have been an outlier. That's one way to completely lose an entire afternoon having done that. Okay, simple random sample, 26th grade students. They were tested on the number of sit-ups that they could do in 1 minute. The mean number of sit-ups that they could do was 36 sit-ups. So 36 sit-ups. Based on data from the U.S. Department of Education. You see, there's something interesting. It's coming from not our sample, but from some other source. That gives us a known standard deviation of 7. So, aha, that means we must use critical Z. So we're going to have to use a critical Z. But it is bell-shaped with no outliers, satisfying that normal condition. So we did have something that was random. I would say that we are independent. Wouldn't you say that there are more than 200 sixth graders out there? So we meet that condition, and we are nearly normal, because that's what they said. It was bell-shaped, no outliers. And so now we're going to use a critical Z, and for 90%, I can't remember what it is, but let's see, inverse normal for a 90%, which would be an alpha of 0.10, splitting that alpha in half, and we get a critical Z Oh, look in your old note packet. Look at the bottom of the table. Critical Z's are going to be listed there. 1.645. Margin of error. My error will be that critical Z times the standard deviation of the population, square root of n. So let's put those numbers in. That was a 7. They could do 7 setups as a known standard deviation. And then square root of, how many kids were they? Do 20 kids? Okay. 2.575. And now we go down to the confidence interval where we add and subtract the error, 36 plus or minus. What did we get for an error? Bring that number down. So I get my 33.4, and I've got mu in the middle. Remember, you're estimating mu. Of course, x bar is in the middle. You used it to make this interval, for goodness sake. That's why you're estimating mu. You already used x bar. With 90% confidence, the interval from, I'm going to use some numbers. Okay, so 33.4 to 38.6 sit-ups captures the true mean number of sit-ups, by 6th graders in 1 minute. Okay, so there's that, and one more problem, and then we get to, maybe some of you kind of know what's coming in this next problem. I'm looking forward to it. This last problem. Okay, fish length. Recorded it was for a simple random sample, 25 fish from Lake Salem. The mean fish length was 7.2. Standard deviation for the sample. It's looking like it might be a T. When examining the histogram of the data, the shape of the data appeared skewed right with a possible outlier. What? An outlier? What does that mean? That means that we don't meet that nearly normal condition to the level where T can do it. So, cannot find interval because of outlier. Well, that was the best page ever. You can't do it with T or Z. You would have to use methods that are beyond the scope of this course. Try your mini quiz.